Abby is a PhD student in geoenvironmental engineering at the University of Alberta. Her current research focuses on incorporating the risk of climate change in the design of mine waste cover systems. In 2024, she completed a Master of Science in geoenvironmental engineering, which assessed the methods for predicting properties of oil sand tailings for capping and reclamation. And let's listen to an abstract for this talk. Capping is an approach to oil sands tailing reclamation, which involves placing materials such as tailing sand or petroleum coke on the surface to reclaim the deposit as an upland or wetland landform. Critically, this requires the tailings deposit to have sufficient strength, density, and bearing capacity. A laboratory testing program and a review of existing published data was undertaken to investigate key properties of oil sands tailing for capping with a focus on the use of indexes to predict geotechnical properties. The results of this research program support the idea that index properties such as Atterberg limit can provide a cost-effective method for long-term monitoring and a preliminary design of cap deposits. And with that, let's welcome Abby to the podium.
Well, thank you very much. So yeah, with this seminar, basically, we're just going to take a little bit of a walk down memory lane for my master's program and go through kind of the overall project and the results. So as soon as I figure out how to advance the slides, there we go. Okay, so as a bit of background, oil sands tailings are the waste product of bitumen mining in northern Alberta. They're produced by the extraction process that removes the bitumen from the oil sands parent material. So these tailings are a slurry mixture of water and soil particles, as well as some leftover bitumen. And then the water also contains ions and other chemical constituents and stuff from the extraction process. So these tailings are initially very fluid, and they're transported to these really large storage facilities you see here by pipeline. Upon deposition, the sand particles settle out to form a beach around the perimeter, and then the water and the rest of like the smaller clay and the silt particles flows to the center to form a pond. And this pond is a very large volume of this slurry material where the behavior is really dominated by the clays. There's a number of different processing techniques like flocculation and thickening that are used in the oil sands to try and improve the properties of these very clay-rich materials. But ultimately, the clays still present a really significant challenge to managing and then eventually reclaiming these deposits. And one step in reclaiming those deposits is capping, which basically means placing a layer of something on top of the tailings. So for example, if the goal was to transform the deposit into an upland or a wetland landform, the tailing surface would likely be capped by placing tailing sand or petroleum coke on top of it. This cap serves a number of different functions, one of which is to create a trafficable surface for equipment to drive on. This is especially important because trucks and dozers and stuff need to be able to drive on top of the surface to place additional material like topsoil and vegetation for reclamation. But if the tailings can't support the cap, the equipment can punch through into the soft tailings below, become stuck or submerged, and this is a very significant safety hazard for both the equipment and whoever happens to be driving it at the time. So when we talk about the ability of the tailings to support the cap and create a cappable surface, the geotechnical parameters that we mainly look at are things like strength and bearing capacity. So with this research program, the goal was to address some of the challenges associated with capping fine tailings deposits and creating trafficable surfaces. So specifically investigating the use of clay index properties for oil sands tailings characterization, assessing correlations between strength and these index properties, as well as assessing methods for predicting bearing capacity. So first, we're going to talk about the clays. So looking at tailings through the lens of clays also allows us to apply existing tools from geotechnical engineering and clay science, one of them being the Atterberg limits. So these are used to describe how the behavior of a clay or clay material like tailings changes as the water content is changed. So at very high water contents, these materials will behave like a liquid. At very low water contents, it will behave as a brittle solid. And then somewhere in the middle, it'll behave like plastic. correctly. And the Atterberg limits define the transition from one behavior type to the next. So liquid limit between the liquid and plastic behavior, and then the plastic limit from the plastic to brittle solid behavior. We also define the plasticity index as the difference between the liquid and plastic limits. And then another handy thing about the Atterberg limits is that we can normalize the water content using the liquidity index. So we define that as 0 at the plastic limit and then 1 at the liquid limit. And this is useful because we can then track where a material is relative to its Atterberg limits. And then it also gives us a common reference scale to compare different types of materials. One of the reasons why Atterberg limits are relevant to tailings is because this measurement can capture changes in things like water chemistry, bitumen, clay content, because changes in these properties will change the measured Atterberg limits. However, because they're casting such a wide net in terms of which properties affect that measurement, it's really difficult to dial in specifically what is causing the change in the measured value. So as part of this research, I attempted to determine how specific changes in material properties and test method influence the Atterberg limits of tailings. So for a bit of context, this is a plasticity chart that shows all of the Atterberg limits that I could find in the literature for oil sands tailings. So on the x-axis is the liquid limit, on the y-axis is the plasticity index. I categorized the tailings into different treatment methods that are used to improve the properties. However, that the main concept that this figure is trying to show isn't necessarily one particular data point or value, but rather that there are a range of values that are possible. So for example, taking the thickened tailings, which is highlighted in those blue circles, we see that there's different groupings of Atterberg limits that have been measured. And those could represent things like differences in clay content, differences in bitumen content, different tailing streams. So overall, the main point here is that it isn't accurate necessarily to define an average or a typical value of Atterberg limits for tailings in general or a specific tailing stream, because the liquid limit and plastic limit capture so many different factors in that measurement. So in terms of the lab testing program, I used samples of both tailings and commercially available clay. So the tailings were centrifuge cake, fluid tailings, and thickened tailings, and these were selected to try and capture the range of different properties and processes that are used across the oil sands region. In terms of their characterization, the key difference between all these materials is that the centrifuge cake and the fluid tailings had quite a high fines content, so a lot of clay, like 90%, 80%, versus the thickened tailings was much lower in terms of its fine content. So a lot less clay, more coarse particles. It had a fines content of like 40%. In terms of the commercially available clay, I used EBK kaolin, which was initially just in a powder that I rehydrated using deionized water, and then I used it for my tests. Tony from our group has previously done some work comparing the behavior of some commercially available clays to tailings. And the rationale of including something like this in the test program is that these commercially available materials have a fairly consistent properties to them. You can just buy them on the internet. So they provide a pretty useful control group and a way to dial in lab procedures for a program like this. So for the Atterberg limits tests themselves, my goal was to see how changing different aspects of the material and test procedure would change the measurement. So looking at test procedure, I used both the Casa Grande cup and the fall cone for the liquid limit, and then plastic limit, I just always did the thread rolling method. For the tailing samples, I looked at the effect of drying and rewetting. So all of my tailing samples were initially at water contents that were well above the liquid limit, so very, very fluid. So first what I did was I just put them on the lab bench, dried them at room temperature until they reached the liquid limit. I measured that, kept drying them until they reached the plastic limit, measured that. And then with that same sample of material, I just added deionized water so I could measure both quantities again after they'd been rewetted. The last test is for what I called amended samples. So these were samples of tailings that I had shipped to a lab to undergo some kind of processing. And then I had the solids shipped back to me so I could do Atterberg limits on them. The amendment methods I used were Deanstark and coal extraction, because these are existing methods that are used to remove bitumen from tailing samples. And the process itself changes the properties of the material a little bit. So I was interested in seeing how that change would show up in the Atterberg limits measurements. So this is just a general plot of most of my results on a plasticity chart. I have the range of the measured tailings values stated on the charts, and we can see that it does kind of look like differences between the tests cause differences between the Atterberg limits. However, looking at all of this together, the question becomes, is this actually significant? Can we make generalizations about how changing different properties, so like bitumen, clay content, whatever, how that changes the Atterberg limit? And the answer to this, in my opinion, is actually no. Not to say that I wasted my time, but the results are what they are. And the reason why I'm saying that you can't make these generalizations is because Atterberg limits are highly variable. So they're not very precise. These histograms represent the distribution of the percent difference between duplicate measurements from the literature. So they performed liquid limit and plastic limit tests on the same sample of tailings, and you would expect to get like the exact same result because they're duplicates. But in fact, while you typically get a fairly low difference between the duplicates, you can really get a range of values that are possible. So comparing my results to this, it wasn't exactly clear if the difference between two data points in my test where I changed something was significant or was just the result of like the measurement uncertainty that can happen between any two Atterberg limits tests. So the overall conclusion here is that while I think there's still value in performing Atterberg limits tests because they're quick and they're straightforward, they capture a lot of different properties in a single measurement. Because there's so much variability baked into these tests, exactly what is causing those changes, and then by extension, how a change in properties will affect the Atterberg limits can't really be reliably determined. However, another reason that Atterberg limits continue to be relatively useful, despite their limitations, is that they can be used to develop correlations between other properties. In particular, correlations between remolded undrained shear strength and liquidity index, which again, water content relative to the Atterberg limits, have been around for decades for different kinds of clay materials. Locat and Demers developed a correlation for sensitive clays in Quebec, and this was previously applied to oil sands tailing. However, there are a couple of problems with applying this relationship to tailings. The first is that this relationship was developed for sensitive clays in Quebec. So not exactly oil sands tailings in Alberta, but could make the argument that they're similar. But the other reason, and this is kind of more significant in my opinion, is that this relationship was developed for materials that are well above the liquid limit. So very, very, very fluid. And when we're talking about capping, it's really not practical to cap things that are like well above the liquid limit because it's just like a liquid. So in order to get any useful information from this for tailings, we're having to extrapolate it pretty significantly back to between the liquid and the plastic limit. Sometimes I do worry that I'm kind of picking on this relationship too much with this research because they really did not ask to be dragged into tailings reclamation discussions. We can see from the plot, it really is a great relationship for what it's for, but it's not for tailings. So as part of this research, I developed a correlation for tailings specifically using those same samples that I did for the Atterberg limits, and then did that using the ball cone. So on the, I think, left, whichever side of the slide. And this is the results of that work. So on one side is the remolded strength data plotted against the water content. And then on the other side is the same data points, but the water content has been converted to liquidity index. We see that all the results actually collapse pretty nicely into a very clear trend. So the bold black line is the equation I've proposed based on my results. and it does seem visually to be performing better than the Lokan and Demir's relationship. I will take a moment to add some complexity to this though, because you'll recall that just a few slides ago, I was saying that Atterberg limits are not super reliable, they're very variable. So while this relationship is an easy way to estimate strength properties from index properties, it is an estimation, and actual strength measurements are always going to be more appropriate than something like this. And some of that complexity is illustrated on this slide here. So with these plots, I'm trying to demonstrate what happens if you use the wrong Atterberg limits to apply this strength liquidity index relationship. So for example, using the Atterberg limits from the Dean-Stark method amended tailings for like as received tailings that have been just dried down. The numbers here aren't really all that important, but the key message here is that if you are using Atterberg limits that are off to calculate your strength values for this relationship, your strength values will also be off. And again, Atterberg limits are highly imprecise, so getting the right number is often a little easier said than done. So on that cheery note for caveats, I will say this new relationship actually fits the Lave spec quite well relative to the Lokan and Demir's. I'll note that there is not a lot of high quality remolded strength liquidity index data publicly available. So it was difficult to compare the fit of the model to data that was not used to develop the model. So I'm quite interested to see going forward, this gets stress tested with new data from other labs. This discussion on strength leads us into bearing capacity, which is one of the other geotechnical parameters used in capping design. So a common way to estimate bearing capacity in the context of capping oil sands tailings is using peak underhand shear strength. So the equation boxed in blue up there. So since peak and remolded strength are linked by the sensitivity ratio, this implies that we can link the relationship between strength and liquidity index that was developed before to bearing capacity. So for the final stage of my research, I investigated the performance of these different methods for predicting bearing capacity. I did this by performing model footing tests on samples of centrifuge cake, EPK kaolin, and thickened tailings. So identify these in a Tempe cell by applying an air pressure, and then by varying the air pressure, I got samples of a few different water contents. I then measured the bearing capacity using a model footing test where a pocket penetrometer was used with a triaxial loading frame. After that, I used the Falcone to measure peak and remolded strength. So in total, for all of these samples, I measured bearing capacity, peak strength, remolded strength, sensitivity ratio, and then water content. And then that water content could then be converted to liquidity index. So this slide shows how the measured bearing capacity compared to the bearing capacity predicted from the peak strength. You can see that they generally match pretty well. So some of the thickened tailings is just kind of floating way out in space over there. My hypothesis here is that if you recall, the thickened tailings had a much lower fines content relative to the other types of materials, and that seemed to be the most significant difference from the characterization. So the hypothesis here is that maybe that's causing a different pattern of behavior, but I didn't specifically investigate that. So this slide shows how the measured bearing capacity compares to the bearing capacity predicted from that sensitivity and remolded strength. So again, the thickened tailings is being kind of wacky, but the centrifuge cake and the EPK actually matched surprisingly well. So this then brings us to this chart. So this is a general chart that relates the liquidity index, sensitivity, and bearing capacity. So these parallel lines are different sensitivity ratios. And the use case for a chart like this is that you can estimate the bearing capacity from these index properties. And again, the keyword here being estimate. So this also links water content and bearing capacity. So potentially you could use this with something like a consolidation model to estimate the amount of time you needed to reach a target water content, liquidity index, and by extension bearing capacity. And this is an example of an application of this, what that might look like. So this table shows the different liquidity indices you would need to support different types of equipment, different sensitivity ratios. That being said, all of the warnings that I've kind of gone on and on about regarding Atterberg limits still definitely apply here. So bringing us to the conclusions, and I'll go through these based on the different themes we've covered today. So regarding Atterberg limits, it was observed that the measurements were affected by the material properties, preparation method, and test procedure. However, as I pointed out, the results don't definitively identify the specific effects of individual properties on the measurement. To actually assess this, you would likely have to do a study where you did a bunch of points for a single method on one type of tailings. But the question then becomes, is it really practical to bound the uncertainty in a test that has so much variability baked into it? Is that result really worth the time and effort? I'd argue actually that the most useful part of this theme was looking at the variability of duplicates versus my own. And this method could potentially be useful in examining other tailings characterization properties. Regarding strength, the proposed relationship between remolded strength and liquidity index does provide a better fit than the Lorcan and Demir's relationship, and all samples showed a similar behavior when the water content was normalized to the liquidity index. However, to actually use this relationship, it assumes that you know what your Atterberg limits are, which may not necessarily be the case, in part because tailings deposits are so heterogeneous. So as a result, sensitivity testing might be needed to actually apply it. And there is also very little publicly available strength liquidity index data to validate this, so it definitely needs to be further stress tested. Finally, for bearing capacity, the existing method for predicting bearing capacity from peak strength provided a reasonable prediction, and a method was also proposed for predicting bearing capacity from liquidity index and sensitivity, and this also performed reasonably well for some samples. However, the behavior of the thickened tailings presents some lingering questions for the use of this model. To address these, the relationship should be tested using lab and field data specifically for low fines content tailings like these thickened tailings. So that is the end of the presentation. Thank you very much to Undertaken and COSIA for the funding. Thanks to everyone who helped me in the lab, and thanks to Dr. Byer for supervising me and putting up with my many flights of fancy in the lab.
Thanks, Abby. Any questions? Yeah. But should I ask a question loud because it's not what it's usual?
Thank you for the presentation. You have mentioned variability sort of intrinsic to the result. And you have shown this variability in different locations. Do you expect much amount of increase if you concentrate in one location? Or no, you don't expect, you don't expect much increase in the precision?
It's a good question. So I'll repeat the question for the Zoom. I think if I'm correct, your question was, would you expect more or less variability? Yeah, if you were just doing tests. Yeah. I think in theory, yes. Because there's like a range of values that are kind of reasonable for a specific type of material. But ultimately, I think it would be very difficult to remove that kind of baked in variability from a test like this. Like you would still expect to have some just based on the myriad of things that can basically make these tests go a little bit wonky sometimes. Yes, it's very difficult to control some variables, and having done a lot of these tests in the lab, I was even finding that if I was doing plastic limit, as soon as I was getting like hungry and I really wanted to leave and go have lunch, the test would go wonky. So things just like your mood seem to affect tests like this.
That's working.
Oh,
so on your slide,
Okay.
you're talking about how think what you were saying was that basically your correlation was not really fitting well to other measured values, is that right?
It was less that it wasn't fitting. It was more that there weren't a lot of other measured values that I could actually compare it to. Like if I go, I do have a slide somewhere in kind of the depth of this presentation, but I only really found like 2 tailings data sets that were strength liquidity index in my whole literature review. And one of them was like kind of really, really wonky. So there's still definitely a big asterisk as to, was this just something that worked for me in my samples, or could you generally apply this?
Yeah, do you think the type of testing, so you use fall?
Yes.
So I mean, survey on remote training lab, we expect the correlation to pan out as well.
It's a good question. I'm honestly not too sure. Most of the other relationships that have been developed for other clay materials, they typically are also using one particular method, like, oh, I used like Manitoba clays on like the shear vein. So I'm not too sure. That would definitely be something to look into. That being said, I did really enjoy using the Falcon relative to the shear vein. Found it a little bit easier.
So where is just the one? So you're doing a PhD.
Yes.
So are you, is that the situation of work? I don't want to.
Yeah. Yeah, currently it's not. I wanted to do something different. So this is sort of kind of a little bit of the end of the road for this research. Maybe it'll get picked up at some point. Maybe someone will pick up this relationship, test it out, feel like it's super wrong. But that would still be very useful information for me to know. I do have data, but does it work generally? That's still a question.
Okay, make that.
So.
Yeah.
So the standard says that you deionized water with your. Right? Let's say if you had used the ionized tailings, you expect like more repulsive behavior into the reaction. So freezing processes.
I would actually have to kind of go back to my thesis to look at that. I did look at all of the different factors that could potentially affect that. You would expect some different behavior, but I cannot remember off the top of my head which one it is, and I don't want to lead you wrong.
The first time, yeah, yay. More? No? Okay, so I think that's for today, and thank you.
Another water bottle.
Another water bottle for you.
My water bottle cabinet.
I don't even have everything, there's something else.
This one has a straw, which is pretty exciting.
Yeah. Well, there's other here on.
Euro and stuff.